Right, let's look at the section 10.4 continued. This section talks about comparing cardinalities. Comparing finite sets is pretty simple. You just have to count the number of elements and compare. But when it comes to comparing infinite set, we need a new definition, right? Since we cannot count the number of elements. All right, so as we know that we say that the cardinality of A is equal to cardinality of B if there's a bijection, which means that there has to be a function 1 to 1 and on to function from A to B, right? Then we say these two guys have the same cardinality, right? We say cardinality of A is less than or equal to the cardinality of B if there's a function that is 1 to 1 from A to B. Doesn't have to be onto, it just have to be 1 to 1. So if there's an injective function from A to B, we say the cardinality of A is less than or equal to the cardinality of B. Right? Then we have a strict inequality, so we say the cardinality of A is strictly less than the cardinality of B if, of course, it has to be cardinality of A is less than or equal to B. At the same time, we do not allow the cardinality to be the same. So we cannot have a bijection from A to B. So, right? Then we have a strict inequality, right? For example, we just learned that the set of rational number has the cardinality, the same cardinality as a set of all integers. So this would be equality because there's a, and these guys are actually denumerable sets. So these are all have the same cardinality as set of natural numbers. All right. But there's no bijection or bijective function from set of all integer to set of all real numbers. So in this case, set of real number, it has a larger, strictly larger cardinality than set of all integers, right? And a set of all real numbers have the same cardinality as, for example, an open interval from 0 to 1. All right, and next topic is continuum hypotheses. And what is said is that this is a pretty interesting hypothesis. It says that there does not exist, so there does not exist a set, let's call it S, such that the cardinality of S is strictly between a set of all natural numbers and a set of all real numbers, right? So remember that N is a denumerable set and R is an uncountable set. Then you can see that there's no set that is strictly in between, right? So there's a gap between these two guys, but you cannot find any set that's strictly in between the cardinality of set of all natural numbers and the cardinality of set of all real numbers. So this is a kind of an interesting hypothesis, but we take this for granted since we cannot prove it or disprove it. All right, and the next question, a natural question would be, can we find, so we know that the set of all real numbers will have a higher cardinality than the denumerable set. And the question is, can we find an even bigger set than the set of real numbers? All right, we're gonna prove a theorem that allows us to construct a bigger set than any set. We'll go over that in the next video. All right, so that's it. I hope that this was clear.